is the report titled Preparing Distribution Utilities for the Future, Evolving Customer Consumption in RE-Rich Grid, Novel Analytical Framework, and the launch of the Evolve tool. Both the report as well as the tool has been developed under USAID's Greening the Grid program under a specific component called Power System Planning Reforms, which is implemented by National Renewable Energy Lab. The report as well as the tool is a result of an extensive modeling exercise which NREL conducted in partnership with BSES Yamuna Power India Limited, it models the evolution of the system load and solar injection across the BYPL service territory. So you will be hearing more about the tool, the report, as well as the tool from our experts from NREL. It gives me a great pleasure to welcome all of you on behalf of United States Agency for International Development, that is USAID. And let me quickly introduce myself. I'm Monalizia Halsra. I am the Regional Energy Manager and the Clean Energy Specialist. This event, as I mentioned earlier, we are conducting as a part of the USAID's Greening the Grid program, which is a bilateral initiative with Ministry of Power. I'm really delighted to have senior management, senior officers from BSES Yamuna Power Limited, as well as the BSES. So I will not take any further time, and I will move on to the next segment of the program. And I'll request Mr. Singh, Amarjit Singh, to please say a few words. And before that, I will quickly give a quick introduction to Mr. Amarjit Singh. So Mr. Singh is the CEO of BSES Yamuna Power Limited, an electrical distribution utility in New Delhi. Prior to this role, he was the Chief Financial Officer of the BSES Rajdhani Power Limited for over 6 years. Mr. Singh is a qualified chartered accountant with over 24 years of work experience spanning across diverse business like export, contract, and manufacturing and power utility. His area of expertise has been cost mitigation, especially the power purchase cost, which contributes to 80% of the utility balancing. It gives me a great pleasure to welcome you, sir. I would request you to please deliver your opening remarks. So over to you.
Thanks, Monali. I would like to welcome all attendees across the globe for virtual report release and launch of Evolve tool on impact of renewable energy and its mitigation. And a very good morning, good afternoon, good evening, good day to all of you as per your time zone. First of all, I would like to thank US government, US Agency for International Development, and National Renewable Energy Laboratory for collaborating with BYPL for this study. It is heartening to see that whole world is uniting towards making efforts to protect global environment. This is our joint responsibility to make this world a better place to live in and also give better global environment to our future generations. Shifting from conventional power generation to renewable power generation is one of such initiatives. BYPL is a progressing power distribution utility which has not only registered record reduction in AT&C loss level in its area of supply from 63% to less than 8% over a period of 19 years, but also achieved 24/7 distribution of quality power supply. BYPL is also playing its part for this cause by opting to procure and encourage sourcing of power generated from renewable sources. There are immense opportunities and benefits of renewable power, but at the same time, it has its own challenges. Since the renewable sources like wind and solar are very intermittent and variable, therefore the power generation from these sources is also not consistent like other conventional power sources. This variable nature of power generation from renewable sources poses a lot of challenges for power scheduling and power network like grid safety, quality of power, etc. The study being carried out by USAID, NREL, and BYPL on these pertinent issues is in two parts. One, to know the impact of long-term RE generation on power portfolio, like on power planning, scheduling, and power network, and also how to mitigate the same. The second part covers impact of distributed energy resources like rooftop solar, battery energy storage system, electrical vehicle charging, and so on, and its integration with network design, optimization, overloading. Impact of the distributed energy resources on the grid is also very important, because in area like Delhi, the ratio of peak and off-peak demand on daily basis is very high, and peak demand is sustaining only for few minutes, but we have to plan the network for that peak demand. Moreover, if we have to plan the network on n-1 concept, then we have to plan the capacity of grid equal to double the quantum of peak demand, which is there only for few minutes in a year. Creation of infrastructure for short period of peak demand involves huge capital cost and a waste of money. So promoting more and more distribution energy resources like rooftop, battery storage, electrical vehicle, etc. can help in optimizing the network planning in city like Delhi, where there are space constraints also for installation of transformers, grids to take care of load growth requirement. It will also result in optimizing the capex and thus reducing the tariff burden on the consumers. Going forward, this is very important for the future role of DISCOM, since DISCOM is becoming the distributed system operator. Since the report of this study is going to be public, therefore this study will not be helpful for the BYPL only, but it will help the power sector at large and will be a milestone. With this, I would once again like to thank all the partners for carrying out the study and looking forward for many such associations in future for the common well-being of the society at large. Thank you.
Thank you so much, Mr. Singh. As you rightly pointed out, this tool is meant for a number of other distribution utilities, and we are hoping to share the learnings from this particular modeling exercise, as well as talk about the tool, which is an open source tool, which will be very useful for many other distribution utilities. So thank you so much for sharing your remarks. We are really delighted to have BSES partner us for this exercise, not only for this, but we have few other initiative under Greening the Grid with the whole BSES group. So thank you so much once again for joining us today, as well as for your remarks. Now, if with your permission, if we can, launch the report, if you will allow, then we will do a quick short, virtual launch of the report. So do I have your permission, sir?
Yeah, sure, Monali, please go ahead.
Great. So I'll pass it on to, Ripu, if you can please bring up the formal launch of the report as well as the tool. Great. So that was the report as well as a quick snapshot of the tool. Our experts from NREL would be talking soon about the report. So we now move on to the next segment of our program today, and which is the meat of the discussions today. So I will now invite my colleagues from NREL to make the presentation. We have 4 speakers, and let me quickly introduce them. We first have a context setting presentation, which will talk about the results and finding of the modeling study by Adarsh and Shivani, which will be followed up by a technical discussion on the research outcomes and the tool, evolved tool by Marty as well as Kapil. Let me quickly introduce all the 4 speakers. Dr. Adarsh Nagraja, to begin with, is the Group Manager, Power System Design and Planning at NREL, or National Renewable Energy Lab. He manages the group that focuses research on power system design and planning and power system engineering center at NREL, with focus on advanced power system research related to fast-changing energy system. Dr. Shivani Ghosh, who also is from the Grid Planning and Analysis Center at NREL. She serves as the technical lead for several projects at NREL, which focuses on distribution grid planning, design and controls, and integration of emerging technologies, such as what we will be talking about today. The third speaker for the day is Marty Squags, and I'm sorry if I'm getting the last name mispronouncing it. Marty is the Power System Research Engineer in the Grid System Group within NREL Grid Planning and Analysis Center. He primarily works with production cost and capacity expansion model and is especially interested in developing infrastructure with aggressive renewable energy targets. Moving on to our last speaker for this particular segment is Kapil Dwivedi. He is the research engineer at NREL. He completed master's degrees in electrical engineer in Southern Dakota State University and is a bachelor from Tribhuvan University, Nepal. His area of expertise includes distribution, feeder modeling, DR impact assessment, and so on and so forth. So we have a great array of speakers who have been working very closely with our colleagues from the BYPL. And who I, really admire for their involvement in this project, which really shaped up the tool as well as the study. So I'll not, belabor on this. I'll just move on and invite Adarsh and his team to please make the presentation. So over to you, Adarsh.
I think, Monali, let's do a quick picture. The snapshot. Okay. Yeah.
Okay.
We have everyone here.
Okay. Can I request everyone to please switch on your camera, and apologies to all the attendees. Just give us 1 minute and we will quickly do this. Can I request everybody to, and Bhupi, and then just let me know once you're done. Abhishek and Baba sir, if you can.
Tushar, Bhupi, Baba sir.
Bhupi?
Yeah, good.
Okay, so we have all the panel full. If we can quickly take a picture, please smile for the camera.
Yeah, we are done.
Thank you so much, Bhupi, and thanks for the reminder report. I mean, this is the only reminder in a virtual right case. Okay.
No problem. Yeah, let's move on, I think.
Yeah. I'll pass on to Adarsh, who will now be conducting the presentation as well as the follow-up Q&A section which will follow. So over to you, Adarsh.
Thanks, Monali. Thanks, Singhji. It was so good to hear such thoughtful words from on the renewable integration and challenges that are happening at scale. In the meanwhile, we get the slide up for sharing. I will start setting the context. This is a collaboration that we as a National Renewable Energy Lab take extreme pleasure. If I may request everybody else to mute their.
Yeah, Kakuli, if you could please mute yourself. And for everybody's convenience, can we request everybody to please keep your mics muted? Thank you.
Thank you. Perfect. So appreciate that. The challenge here is renewable integration happening at all scales, starting from bulk grid to distributed grid all along. And there are advantages that comes with it, as Mr. Singh so rightly pointed out, and there are challenges as well that come with it. And here is a little support from us as a set of solutions that can help distribution utilities with making renewable integration a little more deterministic, certain, and dependable. May I request Shibani to bring up the slides, please?
Shibani, are you not able to share? Okay, we see you.
Yeah, it's on its way.
Okay.
Thank you.
Yeah.
Perfect.
Adarsh, are you seeing the right slide?
It's the other view. You need to swap the view.
Okay,
Correct.
thank you.
Perfect. Looks good. Thank you. So here is an effort by USAID, supported by USAID, being the grid team, and incredibly supported by BYPL here to help us at least identify some solutions. This is all about renewable integration and the grid. Those are the keywords here. And then we get into how can we help them. Before we get into the tool, I want to thank the team. Let's go to the next slide. We had really amazing support from BYPL, all the way from leadership to very, very enthusiastic operators, grid operators and planners from BYPL. They were all along helping us in answering every question for us in a very, very quick fashion. Thanks to BYPL team, a big kudos for your enthusiasm and support. And also NREL team, we got really lucky with a very enthusiastic team in NREL as well. Here you will hear from few of them, but there were other amazing researchers such as Richard who contributed to this project in a very meaningful fashion. The presentation will be only here for like 40 minutes or 30 minutes, but we did a lot of work. There is a full report on this work available online. All you have to do is go to Google and search NREL, BYPL, and Google will pull you the link of the report for the most part. So please take time to look at the report. We took extreme effort in writing up this report, preparing all the solutions, suggestions, and our key findings there. We will be thankful if you all can. If you have questions, you can reach out back to us. We are always available to further enhance and help you all in using the tools or solutions that we developed all along this project and collaboration. Next slide, please. I'll take a few minutes to set the context here. I'm sure you all energy industry stakeholders are aware of this problem, but I want to still take a minute to make sure that I narrow down to the alley where we helped. Not long ago, few decades ago, maybe at most 10, 15 years ago, the power grid was fairly deterministic. There were conventional generation sources, could be thermal, could be fossil fuel, nuclear, numerous types. And all of them were dispatchable, controllable, the way we want. And there's a whole system that was set up to operate these controllable sources. There was a whole layer of tier of feedback response. Everything was set up. Everything was working as expected. And residential customers and commercial customers or end use customers were supplied with energy as expected. All good and well. However, things started changing with inclusion of renewable energy resources such as solar, wind. That's where the challenges started to pile up on each other. Go to the next slide. And renewable integration started happening at bulk power system scale, which is transmission grid, as much as distribution. So let me break down the problem here. Renewable integration at bulk grid is its own challenges. They come in large scale. In India, there are initiatives that go up to gigawatt scale solar farms, and those gets utilized by utilities which are quite far away. And there are all these agreements in place that get sold, and there are quite a few decisions that utilities have to make prior deciding on whether should they choose to go with the process And even then, how can they plan for these variable renewable resources? As Mr. Singh rightly pointed out, they are intermittent, they are variable, they are not consistent, yet they are beneficial and helpful. There needs to be a set of solutions with which utility can make decisions considering the variability. And there is a solution that NREL built called capacity credit in an achievable way. All of you can use Excel sheets, open source basic tools to just make your decision-making process easier. Next slide. Also, renewable integration started proliferating at distributed scale as well. Commercial customers, residential customers were interested in solar. Solar is a generation resource. At small scale in distribution, in the distributed world, solar integration is not a challenge, but when it happens in bulk, a lot of people putting solar at the same time quickly affects distribution utilities. How? The shape of the load quickly changes. The way utilities plan for so long how to operate their grid becomes different because solar generation quickly chips into their basic load shape pattern and changes it. Next slide. It doesn't stop there. Then comes electric vehicle and storage. Electric vehicle adds extreme amount of load. Storage, on the other hand, mitigates and manages the load better. At the end of the day, as you can see in the bottom right set of graphs here, the load shape has totally changed. Did we expect that to happen? Yeah, but do we know exactly how that will change? That we don't know. That's exactly how we'll be helping as well in this particular project. Next slide. So here, what we'll be doing is, for the rest of the time here, we'll be getting into how exactly NREL, along with BYPL and support from Greening the Grid team here, develop solutions so that BYPL can streamline, simplify, and automate decision making. And this is completely actionable to any other Indian utility. These are all available. We'll give you more details. With this, I will have Shibani take over, and please go ahead with it. Thank you.
Thank you, Adarsh. So hello, everyone. Very excited to talk about this project, which is to help BYPL and other utilities to simplify and streamline this problem of having renewables coming at the grid from two different perspectives. So as Adarsh was pointing out, we have large-scale, gigawatt-scale solar and wind plants. Those are connecting to the transmission grid. And then we see this proliferation of having emerging technologies at the grid edge or the distribution interconnection points. So with those thoughts, we identified two research tracks here. The first one is on the transmission level for looking at gigawatt scale solar and wind plants. So what we did, if I'm being specific here, is developing some solutions and some tools for BYPL and definitely other utilities to streamline this decision-making process and to help them with data-driven decision-making so that the power procurement of these plants makes sense for them and for their clean energy needs in the future. So that's the first research track. And the second one, we will get into the details of this just in a bit. The second one talks about how the overall or the net load would probably look like or evolve as we see more emerging technologies coming at the distribution network. So we looked at solar, we looked at electric vehicles, battery energy storage, integrated all of those, and are trying to assess the impacts of having all these technologies and how that would shape the load up in the future. So all these, for all these analyses, we definitely used BYPL's data. And again, thanks to BYPL team for being so helpful and so resourceful with all the data. But all these are really extendable to other utilities, especially in India, where we are seeing the similar kind of problems, not really problems, like similar kind of scenarios now, and also there's a projection of having more renewables coming into the grid. So with that, I'll just give a very quick overview of the tool, and we'll have Kapil present the tool and have a quick demo at the end of our presentation. So the Evolve tool, this actually looks at the distribution specific problem, the second research track that we are talking about. So for that, what we need to do is try to disaggregate the load from the cluster. Like we can look at the feeder, or we can look at the transformer level data with Evolve tool, and based on that we can have the solar, the electric vehicles, and the battery energy storages all coming together for that particular classes of customers. So we considered residential, commercial, and industrial class types of customers for BYPL service territory. And then we have very sophisticated models for solar and electric vehicle integration, as well as the battery energy sizing, energy storage sizing, and scheduling algorithms. So this is a high-level overview of the tool, and we'll get into the details of that in a bit. With that, I will hand it over to Marty to let us through the first research track, which is looking at the renewable plants at the bulk level. So, Marty?
Great, thank you, Shubhani. Just a quick note, I see some gray boxes on the slide that are covering up. I'm not sure if anybody else sees those, or if there's much that can be done about those.
Yeah,
I see the same, yeah.
Yeah.
We see that. I don't know if Shivani can quickly help it, but if not, then we should just
We can go ahead, but maybe
go
can we
ahead,
just
yeah.
exit full screen and sure.
Let me quickly see.
Maybe
if that
Shivani
helps.
stop
yeah.
sharing and then maybe reshare.
No, it's gone now.
It helps, yeah, it's gone now.
Yeah.
Thank you.
Oh, now
Okay.
there's more.
Thank you.
Okay,
That was the WebEx
okay, good.
window.
Great. So thank you, Shubhani. As everyone has mentioned, there's two main prongs to this research. So there's the demand side, or the net load evolution, that Kapil will talk about. And then there's the supply side, or the utility scale issues with RE integration. And that's what I'll be discussing for the next 15 minutes or so. If you could go to the next, please. So as we discussed, and as Mr. Singh so rightly pointed out, as we add more and more utility scale renewable energy to the grid, we're going to introduce much more uncertainty for BYPL's supply. And that uncertainty will grow as the penetration of renewables increases. So first, in this project, we split up these uncertainties into two main buckets here. First is simply the energy contribution of an RE plant. And so just the total megawatt hours that that plant will produce. So whether it's hourly profiles or seasonal totals or annual totals, we want to get a better sense of how much total energy this plant might produce. And second is a capacity contribution in terms of megawatt. And so this is something that Mr. Singh also alluded to when he was discussing having 24/7 supply of load and making sure that there's a reliable, resilient N-1 power system. So this will become more and more relevant for renewable energy plants as the penetration of renewables increases. And the reason for this is that at low penetrations, there's still plenty of dispatchable thermal resources on the grid that we can rely on to provide firm capacity during peak times. As we phase out those thermal generators, we need to rely on other types of generation to provide that firm capacity during peak load. So this can be things like storage or demand response, but at some point at the high enough penetrations, we will have to count on renewables for some type of capacity contribution. And we're seeing this contribution become more and more relevant as we look at different markets around the world. So from the traditional energy kilowatt hours market to more of a capacity market entering the the field and then taking up a larger share of the total market. So there's capacity markets, also things like ancillary service markets are becoming more relevant. And so this is mostly what I'll be talking about for the next 15 minutes, is how we can discuss variable generation plants in this sort of capacity contribution context. So our solution to these two uncertainties was to equip BYPL with data and tools to reduce both of these uncertainties. So these hopefully can help better inform power purchase agreements when we have a better sense of what these plants might provide to the grid, and also assess the ability of candidate projects to fulfill clean energy needs in the future. So as a demonstration of these tools, we estimated the production potential of 7 new RE plants in BYPL's portfolio. So there was 4 solar plants in Rajasthan, 100 megawatts of wind, so 1 plant in Tamil Nadu, and 2 wind plants in Gujarat. But I just want to emphasize before I go any further, and Adarsh also alluded to this, all of these data and tools are completely open source and publicly available for anybody in this field to use. So while I'll be presenting the results for 7 of these plants, the main takeaway here is that this can be extended to really any distribution utility like BYPL, anybody who is hoping to model an RE plant in the future and understand how it will contribute to your particular system. So the main takeaway here is this extendable to future procurements for BYPL and also future procurements for other utilities. So now we'll move into some of those key results from these 7 plants. You would advance, please. So there's 4 main key takeaways, and they split these up into these 2 uncertainties that I discussed before. Please go to the next. So the first takeaway has to do with the total energy contribution that these plants will provide. So this is really the baseline analysis that we do with these plants. And we generally talk about energy performance in terms of capacity factor. So just as a review, capacity factor is this basic metric that describes the total energy produced or estimated to be produced by a particular plant as a fraction of the total energy that could theoretically be produced if it operated at 100% at all times, right? So that's an unrealistic perfect world, and the capacity factor is a measure of how close to that we will get. So for these particular 7 plants with aggregate wind and solar utility scale, we measured about a 27% capacity factor in summer and a 15% capacity factor in winter. And this is largely due to the fact that wind is relatively dominant here, and of course there's a very large seasonality to wind in India, where with the monsoon having a very strong wind resource, and then the months outside the monsoon has a very weak and variable wind resource. Go to the next, please. So a few more detailed results. I won't go into these numbers. I just like to highlight the 17% penetration by generation that I've bolded here. And this is assuming if these 7 plants had been commissioned in 2019. This is simply a measure of how much of BYPL's load they would have served on a total annual basis. So when we talk about renewable energy penetration, it's generally this type of number where it's an energy, a fraction of the total energy or fraction of the total demand met by renewable sources. So 17% is not, it's not a ton, we're not at a very high level yet, but we're also not at a negligible level. So we're entering that sort of mid penetration level where the capacity credit of wind and solar PV will begin to matter. And of course, BYPL's system is not the largest system out there. So as these plants are procured, this number will increase quite rapidly, I suspect. And in the future, as there's lots of opportunities for wind and solar, we will start to get to those higher penetration levels. And then this idea of capacity contribution will become much more relevant. Okay, go to the next, please. You can, this is an animated slide, I think, so you can skip to and one more. So just, oh, yeah, back, please. So this is how we came up with those energy contribution numbers. And this workflow is actually fundamental to most of NREL's analysis that they do, or NREL's, I should say, large-scale grid analysis. So whether it's a production cost model or a capacity expansion model or a reliability model, all of our models and analysis rely on accurate estimated RE profiles, and they all generally come from the same workflow that's based on this algorithm SAM, the system advisor model that is a flagship techno-economic analysis tool as part of our portfolio that's over 10 years old. And it's based on this fundamental algorithm that will take in weather data, plant locations, capacity, and technical parameters, and output estimated hourly profile. So what's nice about SAM is that it is an open source graphical user interface that anyone can download on a computer and use as an application. It's relatively user-friendly, and all of this data is available through downloadable through the program. So this can be quickly used by anybody to measure an RE profile for most places in the world, actually. But we have data for North America and then lots of places in South Asia, including all of India here. So it takes in solar data, wind data, and then different plant technical parameters that in this case were provided by BYPL, and then it will output estimated RE profile. So that's all I'll say about the energy contribution side of things. It's relatively straightforward and really just relies on this SAM algorithm. So if you go to the next, please. So now I want to spend a little bit more time just discussing this idea of capacity contribution. So we generally talk about capacity contribution in terms of this capacity credit figure. And this is, simply put, a proportion of a generator's nameplate capacity that can reliably serve load. So in traditional thermal plants, this is a relatively straightforward measure. And in order to get at this idea of capacity credit, we can answer the question, for a given generation technology, what can be controlled? So for traditional thermal plants, we can control the fuel we put in, we can control the output, we can control everything except for these unplanned outages. So there's going to be a certain percent of the time, a certain percent of hours of the year where the generator will be on forced outages. And that is uncontrollable, but we can get a predictable sense of how many hours that might happen in. So the capacity credit is solely based on that forced outage rate. So the fewer hours that a generator is out, then the higher capacity credit it will have relative to its nameplate capacity. And this is what's shown in this traditional capacity stack, in that second stack there, where all of our supply is made up of these solid blocks of dispatchable resources, and we have a great sense of how much it can be counted on at all hours of the year. As we move to a high variable generation system, you can see that we still have some of those dispatchable stacks, but on top of that, we have variable generation profiles, so like wind and solar and battery charging. So this presents some more complication, as at certain times of the year, we have enough capacity to meet our planning reserve margin, and we can consider the system reliable and resilient even at an N+1 contingency plan. But at other times of the year or other times of the day, when the resources are poor, then we might not have enough to meet that. So we need to figure out, instead of using these variable profiles in the stack, we need to convert those to a solid capacity credit block, just like we have for these thermal generators. And it's this is dependent on a lot more factors, most notably the correlation of the renewable resource with load. So that's going to be the main driver in how we convert these variable profiles into a solid capacity credit, seen on the right. So go to the next slide. I'm going to describe two methods that we shared that can convert that profile into a solid capacity credit. Okay, please go one more. Right, so our first method is a simple capacity factor approximation. And then you can skip through the next one. Just one more click. Right, so, so this only requires a simple spreadsheet editing tool like Excel. And the inputs are those estimated RE output profiles that we got from SAM, and then hourly load profiles. So it's pretty small, but this is I think this is yearly profiles for BYPL. So you feed both of these into this approximation in Excel, and we can get out a simplified capacity credit for a given generator. Okay, go to the next, please. Right, so this method one, this simplified method involves two main steps. And the first step involves extracting the highest risk hours of the year. Because the overall idea here is to measure the historical performance of renewable energy plants during high risk hours. So peak hours or peak net load hours is generally what's used nowadays. And assuming that that generator will perform similarly in the future during high risk hours. So you're essentially just projecting forward what's happened in the past to what might happen in the future with these plants. So again, measure of performance is the average capacity factor of that generator, but we're only looking at those high risk hours and then assuming that it will produce a similar amount in the future. So we generally talk about net load as the riskiest hours because it's a quick review, and we can go to the next slide. Net load is the total demand with wind and solar subtracted. So here on the right is a histogram of those top net load hours. So each of these gray bars represents the number of hours in that top 10% that occurred in each of at different times of day. So you can see, because this is net load, because we have subtracted out solar PV from the demand curve, there's almost no top net load hours during the middle of the day, and most of them occur in the evening and at night. So on top of those net load hour histogram, I overlaid the solar PV and wind diurnal average, just daily curve, so you can see how they line up with each other. And the main takeaway there is that, and just I think there's one more. Yeah, so there's wind lines up relatively well with net load, and that's why it has a relatively high capacity credit. But solar PV is relatively anti-correlated with net load, and so it has a very low capacity credit. So once again, the way to interpret these percent numbers is that about, say, 30% of this farm in Cooch can be reliably depended on during high net load hours, whereas only 4% of the solar plants can be relied upon during these high net load hours. And one other piece to note here is that Coimbatore has a significantly higher capacity credit, at least in this approximation. And that's mostly a function of the fact that the wind resource in Tamil Nadu in southern India has a much higher correlation with the load in Delhi, with specifically BYPL's load, than the wind farms in Gujarat. So if there was a choice between a wind farm in Tamil Nadu and one in Gujarat, then this might factor into which of those would be more attractive to BYPL system, especially as we approach these higher penetrations, because then capacity contribution will become much more important, or not much more, but it'll become more important than it is now, and potentially more important than a simple energy, or like a levelized cost of energy. Okay, just one more thing to note here. So there's a second method that we use to estimate capacity contribution, and that is our reliability model. So go to the next, please. So I don't have time to go into too many details, but essentially this is a measure of trying to estimate how many hours of the year a system will actually have lost load. So it involves the same inputs as before, but now it actually includes more things like thermal outage characteristics and transmission data. So this all gets fed into our probabilistic resource adequacy suite, or PRAS. And again, this is another open source tool that is publicly available. There's a little bit more spin up knowledge required to run the tool, because it involves a stochastic modeling of the entire system and not just the RE plants. But it ends up answering this question of how much more load can a particular generator serve while maintaining the same reliability level. So I please refer you to the paper for more detail about how this reliability model works. But for now, I'll just move on to the results. So one more slide, please. So we have relatively similar results between the reliability model and this top net load approximation, where again, PV has negligible contribution to the capacity to meeting that planning reserve margin, whereas wind still has a relatively strong capacity contribution, and Coimbatore has the best. Now, a quick note, and this is referred more in the paper, but as RE penetration increases, the actual value of capacity credit will decrease. Okay, and one more slide, please. So just a summary of our key takeaways. I didn't have time to mention the second one here, but this is just almost a public service announcement about when you're using something like SAM to model output, some parameters are much more important than others as they have a much larger impact on estimated output. And wind turbine model and hub height are examples of those parameters that have a very large impact on the output. So in our case, there was as much of a 71% change in total energy produced, depending on which turbine model was used. So it is imperative when analysts are researching and estimating and modeling these plants in the future, it is imperative that we try to gain as much insight into the specific technical details as possible. So that's all I had from the utility scale side of things. And now I'll turn it over to Kapil to discuss the net load evolution. So looking at things from the other side, from the demand side. So.
Before you drop off, there are two questions that maybe we can answer, and the rest we can answer after
Okay.
is done as well. So the question is, what's the source of weather information and how dependable is it?
Right. So I guess I don't need to go back to that slide. So that was the slide on SAM. So like I mentioned, that weather data is fundamental to most of the work that we do at NREL. And there are two main databases that we have entire teams working on to update and maintain that data. So the first will be the National Solar Radiation Database, or NSRDB. And it's a little bit of a misnomer that it's national because there's actually data for many different countries around the world. And the second one is called this Wind Toolkit. And I think it's the WIND is actually an acronym, but then it's the Wind Toolkit. And both of these data sources are publicly available on the RE Data Explorer. And if you just go to re-explorer.org, you can zoom around the world and download data from many different sources. So these databases actually encompass several different sources, and there's various different satellites that are used to produce these gridded data. And they are actually at a 90-meter resolution, but because that's just an incredible amount of data, we have teams that will aggregate that, have an entire geospatial team that aggregates from that 90 meters up to around 3 kilometer, 6 kilometer grid blocks. And they have hourly estimates for about 7 years. So depending on the region, we have between 20 and, well, 1 to 20 years of historical data. And the question is, how dependable is it at the micro level? Right, so this is based on historical satellite observation. So it does include things like cloud cover, other meteorological effects. But I will say that the main downside is that it is all historical, right? None of it uses a global climate model to actually predict future weather patterns. So we're working on this, but it's much more complicated procedure to look at how weather might actually be different in the future due to climate change or other factors that will change atmospheric trends. So I would say it's very dependable, it's very detailed, but it is still based on historical weather.
Thanks, Marty. Second question here is, kind of follow on to the previous. There are these, ramps due to weather. How is that considered or counted in your capacity credit estimation?
Right. So that's an interesting question, and that's actually a whole separate topic that we at some point we've had these biweekly calls with BYPL, and we shared a fair amount on ramping of the plants in the past. but I would say it's all based on the same hourly weather data, and actually there is sub-hourly too that will take into account, you know, quicker changes in cloud cover or wind changes. But when it comes to the capacity credit calculation, it doesn't specifically involve ramps. It mostly just depends on the resolution of the profile that you're using. So the higher resolution, higher temporal resolution you have, then the better you will capture these quick changes in output there. So while ramps are important, it actually, and I still think the kind of the gold standard for capacity credit is that reliability modeling, and that is as accurate as the input profile. So it will actually take all hours together and figure out which are the highest risk hours. And that has more to do with instantaneous supply and demand balancing and transmission constraints and thermal outage characteristics than an individual ramps. So
okay, I see what you are saying. It's the whole effort of capacity credit is to process these short-term changes like ramps into a
right.
Overall capacity credit, a value that you can get out of. That's the
Right.
process. Okay.
And that was the idea with the illustration of the profile that's variable, so that, you know, a profile that has significant ramping, we want to convert that to a single number that we can rely upon.
Correct.
To serve load. So these are the different methods for doing so.
Thanks, Marty. By the way, please feel free to ask questions. We would like to answer questions, so you can put your questions in the Q&A box here. With these two questions answered, let's move on to Kapil's section, and we'll come back to the rest of the questions at the end. We have set aside quite amount of time to answer questions. So
thank you, Alex.
Thanks, Marty. Yes, we do.
Thank you very much.
Okay, thank you, Richard. Thank you, Marty. So hello, everybody. I'm Kapil Diwari, and I will be talking mostly about the Evolve tool and what it offers, how is it built, and we'll give a quick tour of the tool itself. So the Evolve stands for Evolution of Net Load Variation from Emerging Technologies. Can we go to the next slide, please? So on a higher level, Evolve is a software tool that offers visualization and analytical capability to understand the impact of new emerging technologies on especially the net load variation. So Evolve utilizes historical load profile that may not have lots of emerging technologies such as solar, electric vehicle, and energy storage, and gives you an idea of how the load say would change if these technologies were to exist, right? So these four scenarios that you see in the slide is exactly what you can analyze in the dashboard that I will present shortly. The base case is a scenario with little or no DERs at all. And typically customers peak time vary by season. Based on our observation from the load data provided in this study, residential customers tend to peak around late night during the summer and in the morning during the winter, whereas commercial and industrial customers, also known as CNI customers, peak during afternoon. So when the distribution feeders experience penetration of lots of DPV, otherwise known as distributed PV, demand tend to reduce during daytime because of the local generation from PVs, right? On the other hand, electric vehicles primarily consume electric energy. Depending on the types of electric vehicles, whether residential or commercial, demand will increase at different time. For example, if the feeder is seeing increase in a lot of residential electric vehicle unit, demand might grow at night because people tend to charge their vehicle overnight at their homes. Commercial charging stations may see increase in load during the daytime. The utility scale energy storage can be used to manage these fluctuating loads because of the new upcoming technologies, right? So we can use energy storage to discharge it when the load is high and charge it when the load is low. So these are the typical scenarios that we will see in the demo, how we can analyze using Evolve tool. Can we go to the next slide, please? So Evolve uses mathematical and physics-based approach to model these three technologies. So let's look at them individually here. So the time series irradiance data is used, historical irradiance data is used to model the solar output. So user will be able to play with the capacity, and the tool will generate time series generation profile based on that. And along with that profile, metrics such as the total generation at system peak, peak generations, all are included in the tool. So you can look at results specific to each technologies and also the aggregated results. Electric vehicles are modeled using a mathematical approach. Given the number of electric vehicles, Evolve will provide the electric energy consumption profile, relevant metrics such as total consumption, consumption at system peak, and peak consumption during the selected time interval. For energy storage, physics-based modeling is used. Different modes of charging and discharging have been modeled in the tool. And then, so there are time-based charging and discharging, sensor-based charging and discharging methods included in the algorithm. Separate algorithms are also embedded to find the battery size and proper thresholds for charging and discharging. The user will be able to see various metrics related to the operation of energy storage as well in the tool. Can we go to the next slide? So this slide is just to give you an architectural view of the Evolve tool itself. So we have a lot of Python codes developed in this project. So what we did is we kind of wrapped around these different Python codes that we have developed that you see on the bottom of this slide, and kind of develop a higher level interface to all the modules. So if you don't want to use dashboard, you can still go ahead and use these models independently, where you have more controls over how these models will work. So the dashboard is kind of leveraging this higher interface to all the modules and developed around a framework called React. And then so what we have done is we have a backend and we have a front end that is communicating with each other, and we have containerized the application for easy installation. So you can use these technologies to deploy it in the cloud or deploy it in premise, and then use this tool whatever you want. And we have also made it easy to import the new data set if you want, and then analyze those scenarios. So let's go to the next slide. So this is just a snapshot of the tool itself. And then so you can see, you can play with 3 technologies: solar, electric vehicle, and energy storage. Here we just show a sample output with 1 megawatt solar capacity, 10 electric vehicles. By default in the dashboard, we are assuming 25% residential and rest of them commercial. And then energy storage 1000 megawatt hour, 500 kilowatt. And the parameters can be more controlled by just using the backend tool. On the front end, you might see a little bit less knobs there. Okay, so let me share my screen and then go ahead with the demo. So I don't see the ability to share the screen, but
Ripu, if you can please make Kapil the presenter.
Yeah, he should be able to.
cool. Yeah, I can see that. Give me 1 second. Okay. Okay, if somebody can confirm, can see the screen. Can you guys see the screen?
Yes, we can see the screen.
We can
Thank
see,
you very much.
yeah.
So this is the dashboard that I was talking about. So in this dashboard, you can see on the left side, there are control knobs that you can play with, and on the right-hand side, all the results that you can see. So let's take a look at these technologies individually, and then we can combine them also. So we have the data for 2019 here, but you can insert data for other years as well. So I'm going to just display the results for 2019. And you can do it for a daily basis, weekly basis, or yearly basis. So on a daily mode, it will do analysis for only a day that you select. For weekly, you can, it will only select for a week. And then for yearly, it will do for a whole year. Right. So let's do it for a day for now to make it more faster. So if you do it for a year, it might take a couple of seconds there. But okay, so let me do it daily here. And then so you can do feeder wise and distribution transformer wise. If you do a feeder wise, you can select which feeder you want. Right now we have data for just one feeder, but you can add data for multiple feeders and multiple transformers. So I'm going to select these particular transformers. And then you can basically choose. So on the solar side, you can choose how much capacity you want for the solar. And on the energy storage, there are multiple inputs. We'll go over that. But let's look at the solar first. I'm gonna turn off all the settings for energy storage. We'll come back to this. And then, so right now the electric vehicle is 0. And then you have this energy storage 0. We only have a solar. And then we selected this transformer. So let's see how this looks. So if I click submit, then what will happen is, so this is so do TR1. Okay, so you can see that this is the profile. So on the top, you can see how many customers there are for this transformer. Domestic 71, and then you can see non-domestic. And if there are industrial customers, it will also show the number of customers. On the right hand side, you can see the matrix for those transformers. Peak load, how much energy consumption there is. So this is without DER first. And now this is the impact of adding just the solar, right? So the green one is your base load for the January 1st, 2019. And then the blue one is the new load profile. And the solar is basically, this is how the solar generation looks like. And these are the metrics for solar, how much energy is being generated, generation at peak, and all that, right? So you can look at those. And for energy storage and electric vehicle, both of them are 0 because we haven't selected them yet. And this is the effect of DRs. So this is the load duration curve, which is just arranging the load data from increasing to decreasing fashion, right? So what happens if I include energy storage here, right? So if I say I want 20 kilowatt hour with let's say 10 kilowatt battery size. And so if you just do this, and these are the default charging thresholds. So we are using time-based charging and discharging strategy. So we are saying I want to charge the battery at these hours, discharge the battery at these hours. And if you just hit submit on this. So what will happen is, so this is the energy storage. So you can see on the blue line, the storage energy, charging power on the green, and discharging on the red one, right? And then you can see the impact on how much peak power reduced, energy reduction, ramp reduction, average to peak reduction. So all those parameters you can analyze on this one. You can also include energy storage. So if I say, let's say I want for electric vehicles. It'll take a couple of seconds. So this is the energy storage, the electric vehicle energy. So you can combine all three. So right now we are combining solar, energy storage, electric vehicle, and all of that. There are also algorithms here to automatically find the size for a utility scale battery. So if you check on this one, what will happen is it will try to find what's the better size for, what's the size you need to reduce the peak of the load, right? So if you click on submit, it's trying to run that algorithm, and it will basically give you what capacity you need for this one. So it says battery power is 84, battery energy is this, and then so it will recommend that, and you use it here as well on the display. You can also choose these algorithms for finding the best threshold, and if you do that, it'll try to find out, okay, what hours I should charge and what hours I should discharge. It will also automatically find those hours and use that in the model. Cool. So these are the hours, and then these are the capacities, and these are the technologies that you can play with. So there is also one more aspect. So there is a button here called switch screen. So this is just for analyzing the net load variation and the effect of these three technologies on how these parameters will change. But if you switch a screen to profile disaggregation, this is the part that Sivani was talking about earlier on, like, we also have an algorithm to disintegrate the transformer level profile into a consumer level profile. Let's say you have a time series load profile for a given distribution transformer. How would you disintegrate that into a consumer group level profile, like for example, residential, commercial, and industrial. So we have built in a statistical model that takes in the weather data, like for example, temperature, humidity, and also it takes into account a low resolution energy consumption data. So we had a monthly energy consumption data, and then it tries to disintegrate that into high resolution consumer level profile. This might take a bit of time because it tries to run the model for a whole year and it will only display for the time that you selected. But you can still use this tool to disintegrate those profiles. So that's all on this one. Any questions?
Yeah, don't see any questions. We can go back to the thank you slide. And so Kapil, as while you are still talking, so this is like fully open source and anybody can use it, right?
Yes, sorry, I should mention that. Thank you for reminding. Let me go to that link while I'm still sharing my screen here. Give me 1 second. What is this? Okay.
So at
if
this
you
point,
go to
BYPL has already been trained to use this tool, and we have a public link to this Evolve tool. It's a dashboard. The way I described the Evolve to myself is utilities have all this load data. Evolve makes that load data more easily usable and seeable for making decisions. You don't need to look at 8 Excel sheets to make one load profile visible. Now it's this dashboard that can take all of the data and have you look at it in an easier fashion. So this is the link that you all can use. And you want to know how it works, the report has details on how the algorithm individually works. For example, Kapil demonstrated how the storage gets sized, or storage can be automatically sized for a distribution transformer. You want to know how it works, report has the details. So some such details are available for you all. You can always reach to us if you have questions. So here is a web page. Are there any questions, please let us know. Happy to answer. What's the level of, say for example, Kapil, can you quickly answer a question here, which is, say there is a utility who chooses to use this, how quickly is it reconfigurable? How are those dash bullet buttons that we saw is going to automatically change, or
yeah,
how does it work?
So basically, the tool is pretty easy to use. Although you see a lot of dependencies in the code, the installation is very easy. So once you have access to this repo, you can just download the code. You just need to make sure that you have a software called Docker in your computer, and that's it. And this is the simple command that you can use to launch the dashboard. That's all you need, right? And so what you can do is basically changing the data is also easier. You see this folder called input data. You can just go to that input data folder, and then you can increase you can also always add data for the transformer, right? For example, you see the CSV file here. What I would typically do is if you want to add data for more transformers, I would just go and edit this CSV. Right now, I think it has data for only 2 transformers as it's just a dummy data set. But you can add data. So basically just adding one more column and adding time series data. That's all. And then so similarly solar data and other data, this is just a input folder where so this is a lot of data. That's why probably it's trying to let me exit this place here. But as you can see that there is an input folder, and then you can always go and then change those data very easily. And then it will automatically reflect those changes in the dashboard, so you don't have to do anything. So you always read that file and then try to automatically update all the options for you.
Okay, there's a question that came, maybe I can answer this. What DISCOM needs to input tool? All you need to input is your existing transformer load
profile,
feeder head load files, right? That's all you need to input in data. The rest you can choose on the fly. You can go and choose how much PV are you anticipating, how much electric vehicles are you planning or anticipating for, and how much storage if you're interested in sizing storage, or you want to know what happens if you put storage to the load of the transformer. The rest are scenarios. You can give scenarios the way you want. So that's one question. There's another question, let's say here, is rooftop solar versus utility scale solar. So here, you can choose one or the other. It all depends on the size. You choose a feeder head load instead of transformer as the bullet choice. Then you can put utility scale solar for looking at how the feeder head load profile varies or changes when you put a utility scale solar there. So it's possible. It doesn't make the dashboard is or can handle it.
Right, and then one more thing to highlight there is, since we are not modeling the network, so you can basically aggregate all those rooftop capacity and provide it as a lump sum, right? Because there is no locational modeling here, location modeling here, so that's why it's okay
Correct.
to lump them up.
Correct. That's an important factor as well. And another question is, maybe it's related to, let me read the question out here. How to differentiate kilowatt hour purchased? I think this is for Marty, I think. Let's have another question on Marty anyway. Let's go to Marty a little while in a minute here. And I want to re-emphasize one thing that Kapil showed on this tool Evolve. We have a fairly nuanced load disaggregation algorithm for identifying customer load profiles. So that's a very handy tool we have built on this. And even the electric vehicle number that you enter, if you're expecting 100 electric vehicles or 200 electric vehicles in the feeder, taking that number and converting that number into a load profile is a fairly nuanced technique that we have embedded into our dashboard. So the dashboard is so handy, but there are sufficiently nice algorithms running behind it, which you all can trust and use. There's a question here. Distributed solar, all DERs have impact on voltage profile. Does it take into factor? Answer is no. We don't have network topology as input to this. These are net load evolution models. We do not look into that. Whereas in one of the previous efforts with USAID and collaboration with BRPL, we have a tool that is publicly available, which you can use for actually looking at voltage profile variations from these DERs, which has been already done. Very happy to share that link with you if you're interested in that. But this Evolve that we are talking about doesn't have topology information, doesn't have line impedances, or doesn't know where lines are, but only looks at load as the key parameter and the variation the load will take. So that's that. Let's get into questions for Marty here. The question that here I want Marty to think about it, which is the solar or wind locations are far away from BYPL, as you mentioned, like Tamil Nadu, Gujarat. Can you talk about how the question maybe it's coming from is, you look at the weather information. Do you look at weather information particular to Tamil Nadu for looking at wind at Tamil Nadu? Something like that? Like, can you clarify that point?
Sure. Yeah. So I would say, just like in the bottom up in the net load research, transmission is a big missing piece, and that is kind of the elephant in the room. The fact that wind in Tamil Nadu is very thousands of kilometers away from the load in Delhi. But again, this is a much simpler research where we're not looking at network topology or transmission constraints. We are just looking at how the resource itself correlates with demand in Delhi. So yes, certainly the resource is specific to that location, and that the weather source website that I shared before, RE Data Explorer, that's one of the reasons that that's so valuable, is because it has data at every 3 kilometers for the entire country. So you can essentially site your wind farm anywhere, or a theoretical wind farm anywhere, and then estimate how that profile for that resource in that location will correlate with load for your utility somewhere else. So that is definitely the core of this research, is matching wind resource or with solar resource in a particular location with load somewhere else. But of course, we're not taking into account the many factors that are involved with getting the wind power from there all the way up to Delhi, and time of day issues associated with transmission. For that, I would refer you to maybe to the previous Greening the Grid report that came out a few years ago in 2017 that did a full production cost model of the entire country. So for that, certainly transmission was a big factor, and that report discussed what was more involved in transporting wind around the country like that. So
Thanks, Marty. We'll take the last question maybe before we go to closing comments. Let me read the question here. Yeah, most ISOs use wind estimate to be 17 to 24% and solar at 8% as firm capacity. Whereas question here is, how can your study help rise this by actually deferring thermal generation? Mr. Sitapati, you want to clarify this question further, feel free, happy to answer that. Marty, did you get the question, like you want to answer it?
sure, yeah, I would say that is really the end goal here of this capacity credit. You can translate say a 30% capacity credit on a 100 megawatts plant into 30 megawatts of firm capacity that could theoretically replace a 30 megawatt gas turbine, right? So that's the idea here, is that this is one way to decarbonize the grid while maintaining reliability, is to use these capacity credit figures. As for those figures you cited, I'd say most ISOs, that's what they assume. As you'll notice, the wind was significantly higher in this case, and solar was a little bit lower. And that is specific to BYPL's particular load shape. So those numbers might be very different if we looked at load shape for a different area. So Delhi load is somewhat particular, like depends and peaking at different net load peak times. And I would also emphasize that it is very important to look at seasonal differences too. So if the load shape is going to be very different during the monsoon versus in the winter, then the capacity credit may also look very different. So it really depends on just what time of day those high risk hours are occurring and how much wind and solar we can expect during those hours. But I think their intuition to think of firm capacity credit as a replacement for a dispatchable generator is right on point. That's definitely how we think about it too.
Thanks. Guess we are on time, as agenda mentioned here. Thanks to all of you, Shibani, Kapil, Marty, for sharing the content here. Appreciate that. So with this, I will hand over to David. Monali, you want anything to add? Feel free, of course. Thank you.
We'll maybe have Monali introduce David.
Yeah. Although I think David is quite a familiar figure here in India, but I can give a quick introduction to David. So David is a member of the Grid System Group in the Strategic Energy Analysis Center, where he focuses on power system operation at high renewable energy penetration. He's extensively worked with Government of India to help them on the specifically on the grid integration report, which was earlier mentioned by I think Marty, and has been active in supporting the renewable energy targets Government of India's renewable energy targets through these large grid integration studies, as well as these more, expanding or enhancing the capabilities of our stakeholders, Indian stakeholders. So with that, it gives me great pleasure to invite you, David, for your closing comments. Over to you.
Thanks, Manali. So as Manali mentioned, David Polchak at NREL, and I've been proud to be a part of the USAID Greening the Grid program for several years now. I've worked on several studies for this program, but this project with BYPL may be the first time that we've really brought together the issues happening at both the bulk grid and the distributed side with such detail. So I'm very happy to have an opportunity to contribute to this important coordinated planning perspective. And I believe it's a critical perspective that will need to grow within the planning practices for all power sector stakeholders as renewable energy grows on systems in India and around the world. So I'll just provide a very quick summary. I think my colleagues have covered this extensively, but from a high level, simply, what we were trying to do is better understand how renewable energy and clean energy technologies will impact the planning and operation of the grid. So this spanned from the bulk grid considerations, what Marty was talking about, answering questions about how we integrate wind and solar parks into reliability planning, to the distribution side, where we created replicable methods through our new tool so that as distributed resources grow, the impact can continually be reevaluated, and hopefully many attending the webinar today can take a look at the report and get a more detailed understanding of what was done and apply some of these methods to your own context. And I think a number of the questions asked about data inputs, as well as using the tool for specific context, and certainly all these methods were developed with that in mind. So please feel free to use it and improve it and let us know how we can help. So in closing, I would like to first thank Mr. Amarjeet Singh and the rest of the BYPL team for their support and enthusiasm for this collaboration. As my colleagues mentioned, it's been an effective and efficient collaboration, which is not always easy when we sit in different time zones. So we really appreciate everyone's willingness to be flexible throughout this project, and it's been quite seamless. I would also, of course, like to thank USAID and the Greening the Grid program for supporting NREL in this work, and the GTG RISE team for everything they do to keep things moving and to keep us all in line, and the Ministry of Power for their partnership and support for Greening the Grid. This has been successful and fruitful collaboration for all of those involved, and I hope that other distribution companies around the country are able to benefit from this work. Please feel free to reach out to us if you have any questions about utilizing these resources, and I hope everyone has a great rest of the day. Thank you for joining, and goodbye. I think that's the end for us. So thanks again for joining.
Thank you so much, David, and thanks to all the participants. I would also like to quickly thank our partners, BSES, BYPL. So Jitendra ji, thank you so much. Mukesh Dadit ji, Abhishek, again, always, all of you have been very supportive. I would also like to thank Mr. Amarjeet Singh as well as Mr. Sinha for all the support which has been extended to the NREL team and to USAID for the different activities where we have been collaborating. Thank you so much to the NREL team. Great presentation and taking us over the tool. David, Shivani, Adarsh, Mati, as well as Kapil. And finally, last but not the least, very importantly, thank you to the colleagues from GTG RISE, Deloitte, implemented by Deloitte, for all the support for organizing this event. So thank you, ladies and gentlemen. It's pretty late here in India, so have a great night and a good dinner if you haven't got that. But we look forward to catching up again on 28th with another report release and a tool. Thank you so much for joining. Good night.
Thank you. Thank you. Thank you. Thank you very much. Thanks.
Thank you, everyone.
Thank you.
Yeah.
Ready. Thanks for joining.
Thanks, David. Thank you, Abhishek.
Thank you all.